pleasure to welcome Professor Külah to give a nice talk today. I don't think I need to introduce him, but let me briefly summarize his CV. He received the bachelor's and MS degrees in electrical engineering from Middle East Technical University, Ankara, and the PhD degree, again in electrical engineering from the University of Michigan in 2003. And he was employed as a research fellow at the Department of Electrical Engineering and Computer Science at the same university, the University of Michigan. And he joined us, this department, as a faculty member in 2004. He's working on MEMS-based energy scavenging, if I pronounce it correctly, yes. Microsystems for biomedical applications, or in short, BioMEMS, and mixed signal interface electronics design for MEMS sensors. He's a member of Board of Directors and Executive Committee of MEMS Research Center. He was awarded with 2009 Research Encouragement Award by Professor Mustafa Parlar Education and Research Foundation in 2013. Research Encouragement Award by TÜBİTAK, big prestige. 2013 I Am Faculty Award, and well, too many awards Haluk to read. 2015 Young Scientist Award by the Science Academy Turkey, and he received EU Horizon 2020, 2015, means 2015, okay. ERC grant by FLAMENCO project on fully implantable Cochlear implants. So a very big scientist. Okay, I'm sure that you will enjoy his talk. Okay.
Thank you, Professor Geshici, for the nice introduction, and I would like to thank Özgürcan for the invitation today. It has been some time that I didn't present in the department, so I hope you enjoy it. So this is the outline. I will first introduce MEMS very briefly, and then talk about what is BioMEMS and the applications. Then focus on BioMEMS work at our university, what we are doing. There are lots of things in here, but I'm going to focus only on one of them, like cell cytometry. And in the second part of the presentation, I will talk about our ERC project and the latest achievements in that project. So we are working with MEMS Center. Maybe most of you know about it. It is outside the campus, but very close to campus. It is like 1,300 meters square area, clean room with full of equipments. And up to now, there have been, I guess, more than like $70 million of investment there through different kinds of projects. Most of them from defense project by Professor Tayfun Akın. And like there are 6 spin-offs. So the mission of this center is making some devices with added value for commercial applications, for the use of the whole country. So these 6 spin-offs kind of shows that we are trying to achieve that mission. So these are the equipment list over there. This may not mean anything for most of you, but this tells that we can implement any kind of MEMS device in-house. So we are limited by our imagination for most of the time in terms of implementation. There are different works going on in there. The first 3 of them are run by Professor Tayfun Akın. My research is focused on BioMEMS, microfluidics, and energy harvesting. And today I will talk about the work on BioMEMS that we do in our center and in our department. So basically my research areas are BioMEMS, microfluidics, energy harvesting, and of course we do interface electronics for different kinds of devices. We do mixed signal interface electronics. I have a research group, like about, the number is changing, that is between 15 and 20 areas. And some of this work has been result in a spin-off company called Microsystems. I'm going to briefly mention about what they are doing over there as well. So let's start with what is BioMEMS first. Microelectronics, you know it very well. I think MEMS, you know it. Like mechanical structures on top of electronics combined to have some sensors and actuators. BioMEMS is in fact the biomedical application related MEMS devices. There are many different examples for them, starting from pacemakers to glucose meters or brain implants, or like endoscopy capsules, many different devices. But microtests, micrototal analysis systems, and microfluidics is an important sub-part of BioMEMS because it enables to analyze blood samples or any body fluids in a very short time with low cost. So it enables lots of diagnosis and therapeutics. So it's sometimes called as lab-on-a-chip systems. So what we do is mainly focused on this area. So this is the map of the research going on in my group. When I first came here, I started with electrophoresis. We are trying to separate DNA to measure mutation in DNA, for example. Then we start working on playing with cells. We want to isolate cells, manipulate them, play with them, try to count them. For example, early diagnosis of cancer detection, let's say. And for counting, we developed many different systems, including electronics and mechanical systems. We implemented them, they work very well. By using similar structures, we implemented bacteria detection systems. Bacteria detection is an issue nowadays, as you may know. A typical culture takes like 48 hours. But by using such microsystems, you can analyze the bacteria in 6 hours, less than 6 hours. And it is especially important for diseases like sepsis, or like intensive care unit diseases. This fully implantable cochlear implants I'm going to mention about it a lot. And it's like, in vivo device, which is implemented inside the body. And also, besides that, with Hacettepe University Medical School, we are working on different types of neural probes. So there are lots of things that are going on in the group. Today I'm not going to mention all of them. I will only talk about the cell separation part and its applications, and then at the second part I will talk about this fully implantable cochlear implants. So let's talk about cell cytometry. Cell cytometry means that, classifying the cells, and this classification can be in many different ways. You can classify the cells in terms of their size, mass, morphology, or even because of the electrical parameters. As an electrical engineer, this part is more important for us because by using very well-designed circuits, we can measure a little bit differences in capacitances, resistances, so on and so forth. So we can classify cells by means of different electrical parameters. Besides this, people are using some kind of traditional techniques like surface or other antigens to separate them. In fact, there are many more depending on the application. But when you take a look at it, there are two important components. First of all, you want to separate the cells. While doing this, then you can use mechanical structures, electrical or magnetic, and then you need to detect them. And optical, mechanical, electrical techniques can be utilized as well. So here's an example from the literature realized by a Turkish professor in MIT, Professor Mehmet Toner. What he's trying to do is, he has a microchip. It's very hard to call it like a microchip. The size is big, but that's the general case for BioMEMS. What he does is, he puts lots of pillars and coat those pillars with some antibodies which are capturing the cancer cells, for example. And the blood sample is run through these pillars. And the pillars are going to capture only cancer cells, but not the other cells. And then by using fluorescent staining, by using an optical microscope, they are counting the solid cells. And by this way, they tell about what is the stage of the cancer, or is there a metastasis risk, or so on and so forth. This is an example, but when we started this work, we said that we don't want to use any optical system. We want to make everything on chip without using any fluorescent staining, any optical system, any fluorescent microscope or whatever. So that was the main intention. And unlike maybe more than 10 years ago, we started with this separation by electrical means. There's a phenomenon very well known in the area called dielectrophoresis. By the way, phoresis means separation. Dielectrophoresis means separation by using dielectric properties. So the idea is this: if you have an ununiform electric field, and if you have a particle in there, the particle observes some force called dielectric force, and it starts, moving in one direction. And depending on the medium and the particle properties, this force direction as well as the magnitude may change. So this is a very critical and important thing. Like, it has been found maybe more than 120 years ago, but at that time people couldn't apply it, because to be able to do this, they need a huge electric field. And having a huge electric field was not that easy. When the MEMS was first found, then this became realizable. They have very tiny electrodes, the gap is very small, they apply 15 volt, 50 volt, whatever achievable voltage levels, and they have the huge electric field to separate these particles. And the use is this: like, if you have 3 different types of particles, by controlling the electric field in here, by the way, the electric field is AC, you apply some frequency, and if you control the frequency, you can separate them, like this one. This is a very general diagram showing the separation. And you can treat the cells like particles. People are modeling cells with the cell membrane, and cell, what is inside the cell also can be modeled like a sphere. And what they say is, for example, if they change the electric field frequency, and if they have 3 different particles like this, if you apply the frequency at this point, for example, the blue one will stay stationary, and then, I'm sorry for that, the red one will observe a positive the electrophoretic force. The other one will see a negative one, and you should be able to separate it. And there are different applications for them. For example, this is our early trials. This is the blood sample. Red and white cells are all together. When you apply the electric field, red cells are accumulated in some part, the white ones are accumulated in the other part. So the theory is kind of like somehow matured. And they say that this dielectrophoresis depends on cell radius, cell properties, and the medium that you use. And they have this frequency chart. And the interesting thing in here is that tumor cell lines are separated very well from the normal blood subpopulations. So if you can find this region for operation, for example, then theoretically you should isolate tumor cells from the normal blood subpopulations. And we work on this thing. We design such a chip. This is the top view of a microchip, let's say. It's not the exact view, of course. This is just a schematic. What we do is we have the blood sample coming through here, and there are some V grooves in here, forcing the cells to go through the walls. At the walls, there are 3D electrodes. You apply some frequency, and because of this frequency, you capture the cells. And this simulation shows that, for example, one sort of cell cannot penetrate through the channel. They are captured on the walls. The other type, for example, can pass very well. So you can choose these 2 types as you wish. So these are the fabricated chip photographs. As you see, it occupies like 1.5 centimeter by almost 1 centimeter. Very tiny one. It's a closer view with the V-channel, the V-shaped obstacles. So where we can use this thing, we can separate, as I said, 2 different particles, 2 different cells. Let's think about a cancer patient. He or she gets some chemotherapy, and during this chemotherapy, the physician waits for 3 months or 4 months. And if the chemotherapy does not work, they have to start a new chemotherapy cycle with a different drug. And it's like a pain for the patient as well. So if you can notice the effectiveness of that drug on the cell, then it can be a quite big achievement for the patient. At the beginning, you can take the tumor sample and you can say that, okay, this drug is not going to work. Try the other one. So you are going to save at least 3 months to the patient and the physician. And when we analyze them, you see 2 different types of cells. You don't need to know the biology in here, but the basic idea is this. If a cancer cell is sensitive to a drug, its membrane property is a bit different, results in different electrical property. So the same story that I mentioned, you have 2 particles, they have different electrical properties, so you should be able to separate them from each other. Here is the example. you see leukemia cells, K562. These are drug sensitive, these are drug resistant, and DR means multi-drug resistance. If you take a look at under microscope, they are the same, no morphological difference. But we know that they have electrical difference. So here is a video, real-time video taken in our lab from a microscope. You will see a movie in here, and there's a channel. And in the channel, there will be K562 cells moving around. And when we apply the potential, you will see that we collect them on the walls. It started. Flow rate is like 10 microliter per minute, and the cells are passing like thunderstorm. You will see them much more clearly, I guess. The voltage level is not high enough right now. When you increase it up to 10 volts, you will see that accumulation of cells in here. They're still passing quite fast. So when we apply 10 volts, as you see, we start capturing the cells. And the number of cells are too much, so the area is saturated, and the rest of the cells are moving away. Here is a more controlled experiment. Now we mixed resistant cells with sensitive cells with a ratio of 1 to 100. If we have one resistant cell, for example, there are 100 sensitive cells in the sample. And we color the sensitive ones with green fluorescence, the other one with red fluorescence. Again, a real-time video, the channel is here. And we take a look at the channel with different filters. At a time like red filter, the other time with green filter. So theoretically, at the red filter we should see captured cells. At the green filter, the environment should be clear. So like capturing started here. And if you take a look at it in the green filter, it's like empty. Nothing is captured. So we captured the resistant ones, but not the sensitive ones. And we can model these cells much more like scientifically. What is the proper frequency, what are the dimensions like we should care for, or electrical parameters, and we come up with this chart. And we show that we can detect drug resistance in cancer, especially for breast cancer and leukemia, at an earlier stage. And then we talk about this question. This chart, we got it from the literature. But we noticed that it's not that reliable because people are using different cell cultures, different cell types. So this chart sometimes gives us some, unexpected results. So we start working on modeling the cells and how we can model it. There are some nice movies in here. Maybe you can see. There's a cell in here. The cell is rotating around itself. And what we do is, in fact, we put this cell in 4 electrodes and apply signals with out of phase. And because of these signals, the cell starts rotating. It's very funny. But what is the good news about it? This rotation rate gives some information about the cell property, like cell dielectric constant, membrane dielectric constant, that kind of stuff. So we fabricated different types of these devices for electrorotation. Test all of them, one by one. And by using some image processing, we try to get the mid part of the scope area, or microscope area, to get a better result. And here is the movie taken from the microscope. As you see, the cells are rotating, and one of my grad students were counting them by eye, by their eye, and he was like this all the time. And then at the end, because of at the end of these all measurements, we got a chart for different. This is for leukemia cells, for example, drug-sensitive leukemia cells. We got the membrane capacitance, effective conductance, and so on and so forth. And these results are quite valuable for further experiments. We did the same thing for imatinib-resistant leukemia cells, or doxorubicin-resistant leukemia cells. So we had a good database for further analysis. As you see, breast cancers with doxorubicin resistance, leukemia with imatinib resistance, and all the cell parameters are somehow obtained by using this technique. So, we did lots of things similar to this one by using these microchannels and microelectronics, like bacteria detection, cell separation I mentioned. And this MDR detection, drug resistance detection, turned out to be a spin-off company, Microsystems. I just want to mention about what we are doing there. It's also a high-tech research and development company. We are working on this drug resistance detection, and at the same time we do some circulating tumor cell detection. Let me mention about it very briefly. Cancer, it's a very critical disease nowadays, but most of the time, metastasis is the killing point. 90% of the cancer patients are dying because of metastasis. So if we can detect the metastasis earlier, then we can increase the life expectation for cancer patients. And for this purpose, people are working on something called liquid biopsy, because solid tumor biopsy is invasive. And sometimes the physician may not even touch the tumor because of many different reasons. So people are trying to capture circulating DNAs, cancer cell DNAs, or circulating tumor cells, the cells itself, or some exosomes coming from the cancer cells from the bloodstream. And they claim that this is an approach, and FDA approved this approach as a technique for early metastasis detection. But the challenge is, you are looking for very rare cells. I give this example like this. You have a very big number of sugar, for example. You just put 10 to 100 particles, salt particles. You want to identify them, isolate them, and count them. It's a very challenging process, I guess. The same thing goes in here. If you take 1 milliliter blood, there are this much red blood cells, platelets, white blood cells, and you are looking for only 10 circulating tumor cells. That's a big challenge. And many people are working on this in terms of CTC, DNA, and other types of analysis. But unfortunately, there is no satisfying solution providing high specificity or purity, ease of use, and proper results. So what we claim is, we try to solve this problem with a 3-stage chip. What we do is, at the first stage of the chip, we do size-based separation. The cells inside the blood ranging from 3 micron to 30 micron, let's say. And cancer cells tend to be larger than 12 micron. So if you can eliminate any cells less than 12 micron, this means that from that big chunk of sugar, you can decrease this thing to 100 grams of sugar. So the probability may increase then for capturing the exact cancer cells. So that's what we're doing here. This is like a quarter of a spiral microchannel. There's an impact whole spiral microchannel in here. With a pressure, we flow these cells in here. Because of the pressure, the cells are moving with some speed. It's like cars going in the rush, for example. The smaller car tends to be inside, the larger car tends to be outside. So it's something like that, but since it is microfluidics, it happens in the reverse way. The smaller cells stays outside, the larger one stays in the inner part, for example. And when you have a wall in between, you get rid of the small cells and you eliminate any cells less than 12 micron. In the second part of the chip, what we do is, we have another channel with many pillars, and these pillars are coated with antibody, EpCAM, which is only sensitive to cancer cells. They only capture cancer cells, but not the white blood cells. So the remaining cells are flowing through here, the cancer cells are captured in here, and non-cancer cells are assumed to be flowed away. And at the next stage, you send another fluid and release this cancer cell as well. And while these cancer cells are passing through the microfluidic channel, by using an electronic chip, you count them one by one. This is like an impedance meter. When the impedance changes, the count is like 1. You say 1 cancer cell passed, 2 passed, 3 passed, whatever. And you can do even more than that. This CMOS chip can notice which type of cell passed through here. Is it really a cancer cell or white blood cell? So you can give a ratio, like I got 100 cells in here, 70 of them are cancer cells, 30 of them are non-cancer, so you can notice the physician accordingly. And at the end, you provide the physician alive cells, alive and pure cells. What is the beauty of it? The physician can culture it, can get some DNA analysis, and because of that, this may lead to precision therapy. So depending on the patient, whether there will be a metastasis or not, or which kind of chemotherapy should work, these kind of questions can be answered with this system. So at this point, we finalize the analytical test over there. The next stage is having some clinical tests. Last month we put one system in Acıbadem Hospital, so they are trying for us. Next month in Austria, Medical School of Vienna is trying the device as well, so they will get some results and they will tell us whether the system is working as we expected. And at the end, of course, what we want to do is we want to get regulatory or FDA approval for further commercialization. So we have a very strong team like you guys. These guys are graduated from electrical engineering department, did their PhD at let's say, one of them is at Switzerland, came back and working in this high-tech team. And another good thing is that this slide is prepared by a French company doing research analysis, the market analysis for such systems. They identify more than 30 companies working for this question, and they select us as well, trying as a player in the CTC market. So this first part summarizes what we do in terms of microfluidics, what is cell separation, cell isolation, why it is important, what can be the application, how can we use. In the second part, I want to talk about a different topic, this FLAMENCO project, which is the acronym from fully implantable cochlear implants. I mean, people are wondering about this acronym. How did I find it? How did I find it? There's acronym generated in the websites. So you enter the project name and then select the proper names. So our next application named as Opera. This is not a joke, by the way. This happened last month. So what does this FLAMENCO does? So let's start with the operation of a healthy ear. So in the healthy ear, the acoustic signals are coming inside the ear canal and vibrates the eardrum and ossicles. The vibration is transferred inside the cochlea. And inside the cochlea, there are tiny hair cells. They start vibrating and they create electrochemical reaction and the hearing occurs. When these cells are lost, hearing is disturbed. And the only solution today is the conventional cochlear implants. They have some microphone at the outside. Maybe I should stop in here to explain more. So here is a microphone. The microphone picks up the signal and then codes it. By using an RF transmission, it's transferred inside the skull. There is a cochlear electrode which is surgically put inside the cochlea. And then they stimulate the auditory nerves by that cochlear electrode. But the problem is, this system is energy hungry. They have to replace the battery of this outer device almost every day because they are using a typical radio system, an RF transmission. And the other problem is, there's always some external part outside the body which is not good, especially for teenagers. Little kids like 3 or 5 years old, they don't want to use it. Even if they use it, sometimes they lose it. And it's like 20,000 euros, by the way, for each implant. And when it's lost, the family should buy another one and match it with the inside implant. So let me continue the video. What we claim is we can do everything inside the body by mimicking the hair cells that we mentioned before. So we claim that we can put some chip inside the middle ear. You will see what is inside the chip. And then by using some electronics to condition the signals and send it to cochlear electrode to stimulate the auditory signals. And this chip has another function. It can scavenge energy to recharge the battery. And how it works? As I said, we are mimicking the natural ear hearing mechanism. This is going to open soon, and you will see cantilevers in here. They operate like hair cells. They are sensitive to a specific frequency. When the vibration comes, they can generate energy, electricity, and the signal is transferred through the IC to the corresponding auditory nerve part. And these are only for transducing, but the upper part is only for energy harvesting. It has a reserved band. So the person listens a tone with a high volume at night time, for example, but he or she doesn't hear because he's already deaf. So with that signal, high level signal, you energize the battery, and in the morning the patient continues to use the device. So when you take a look at it, there are different parts in here, like transducer and the energy harvesting chip. This can be located either on the eardrum or on the ossicles somewhere in here. The interface electronics, this is also quite challenging because you want to do ultra low power design because your power budget is very limited. Conventional techniques are using like tens of milliwatts of power, and we have to go below 500 microwatts. And this thing both generates the signal for nerve stimulation, and some part is generating also the power for the rechargeable battery. So, to summarize, we have the transducers for both sensing the sound and energy harvesting. We need to do integration on a flexible substrate because packaging is an issue. It should be biocompatible and stay in the body for many, many years. The interface electronics, both for nerve stimulation and battery charging, should be low power. The design is another challenge. While doing this test, before the animal test, we have to do everything outside the animal or the ear. So we have to develop our artificial tympanic membrane, modeling the actual ear. And we should do some in vitro and in vivo tests by using animal experiments. So let me mention about them very briefly, how they look like. So this is the energy harvester chip. We use a special technique in here because piezoelectric materials are generating energy, but in macro scale, bulk PZTs are providing better energy. If you go in micro scale, you lose lots of energy. So what we're doing here, we combine bulk PZT material with microscale chip without losing the performance. Still, this can provide enough voltage or current for energy harvesting. The transducer chip looks like a similar one, again piezoelectric one, but in this case, the voltage level or power level is not important. This is just like a frequency sensor. It's behaving something like a music box. Exactly the same thing. You see the cantilevers in here. When you touch them, they create the melody. In this case, you do the reverse. You vibrate them with acoustic signal and they generate energy. Something like that. So these are fabricated by metal. And here's a closer view. Like the device cross-section looks something like this. This is the fabrication technique. And we fabricated them and we got pretty good reproducible results. So this is the fabricated wafer photograph with many different energy harvester chips. So what we showed is that like up to now we can achieve 60 microwatts in air environment with a resonance of 590 Hz. But we are using many different frequencies and many different devices. The aim is to achieve more than 100 microwatt at the end of the project. And we do the test on a shaker table initially, then on the artificial tympanic membrane. For the transducers, again, this is the fabrication method and the cross-section. We use thin film PZT in here with 8 different frequencies. So these are the result at 8 different frequencies, the generated voltages. The criterion here for the interface electronics to work, we should get at least like 100 millivolt of signal, and all the channels are providing that signal at the desired level. The next thing is combining them like a single chip. So these are the drawings for that. The acoustic transducer and piezoelectric harvester, and it should be kept with a recessed die. They should be located on a flexible substrate. And while doing this thing, we don't want any wire bonding because wire bondings are dangerous. They can get broken. Everything should be quite compact. For that purpose, we are using true silicon wire contacts. And we develop it in-house as well. So, like true silicon wires, these are generated by our group members. So So this is the final device. As you see, the flexible parallel substrate, 2 layers on top of it, and you don't see any dangling wire bonds or whatever because all the electrical signals are carried inside the silicon by using TSVs. So this is another version of it, like this flexible cable touching at the top to get some of the electrical signals as well. And it's connected to a ZIF connector to test it further. As I said, interface electronics is a challenge because it has 2 parts, both energy harvesting, both for energy harvesting and both for stimulation of the auditory nerves. I'm not going to go into the details, but the basic idea is it's very low power because we are not utilizing the conventional technique. What we do is we have the piezoelectric cantilevers like bandpass filters, then we have the logarithmic amplifiers, and at the end we have a nuclear controlled current source. This current source is stimulating the nerve with the required amount. So you can stimulate the nerve at different levels, like at 8 different levels, for example, depending on the incoming sound signal. So this allows fitting, which is known as, from patient to patient, hearing level may change. So when you put the implant inside, the patient may not be happy with the sound level. You should be able to play with it like an equalizer. So this kind of architecture helps us to modify different frequencies at different levels. So at the end, these signals are applied to the nerve. The nerves are seeing this kind of biphasic signals. So we test them in such an environment. So this is the artificial ear canal and tympanic membrane that we have. On it, we put the chip with single tone PZT sensor. This is dB meter, and we apply the sound from here. Sound comes, vibration is transferred inside the ear canal, and then this sensor starts working. The electronics is located somewhere in here. And on the scope screen, you see the biphasic pulses for nerve stimulation. So here is a video. Some of you may like it, some may not. Sound level is not good enough. I have to open it more. So what you see is this. This is the ear model. And this PZT sensor is turning on the left. And this was maybe 2 or 2.5 years ago, very early stage. This is somehow, this may not mean anything because the real results can be shown like this. This is the output taken from the chip. And this sentence is used for most of the European doctors for checking the quality of a cochlear implant. They apply this sound, a white silk jacket goes with any shoes. They expect such a graphic at the output of the computer. And this is the generated signal from our system. So as you see, they are quite similar, although there are some differences. But the thing is a person with some training can notice each word or even the sentence. So we are not very far away from the final result this shows. We also do energy harvesting interface electronics. I'm not going to go into the details of that, but I just want to show you some animal test results to save your time. But we tested them, they were working properly. And if this energy harvesting is not working properly, we have the B plan, which is by RF transmission, we want to power up the system. Let's say that this vibration-based energy harvesting didn't work, or the power is not enough, so what are we going to do? The challenge is we can still apply energy from outside by using RF induction. So we also work on that and get some results on that as a B plan. So, but at the end, we did some animal tests. So here you see a guinea pig. And at the beginning, we make sure that guinea pig is not hearing anything. Unfortunately, we make it deaf by using some drugs. And how we measure the deafness level? By using AVR. So by taking some brain signals out of the skull, we can say whether the guinea pig is hearing or not. Then we prepare the setup the second generation of artificial eardrum, and the chip is located in here, our chip, which is sensitive to 1 kHz sound signal. And then the electronics is located in here. It looks pretty much big, but it's only for test purpose. Like after finalizing the test, it can be encapsulated in a very small, tiny black box. So it's implantable still. And then the cochlear electrode is located inside the cochlea of the guinea pig by surgeons. They do it for us. And then we start applying signals at different sound levels. When they apply 1 kHz at 50 dB, no hearing. 55 hearing starts, like up to 100 dB, we can have hearing signals from the guinea pig. If we apply a signal out of band, like 3 kHz, which our sensor should not respond, as you see, nothing is measured. So this somehow shows that the guinea pig can hear our 1 kHz sound signal. And we repeat this test for 4 different frequencies by using 2 channels, because the ultimate goal is covering the whole frequency band, like 8 channels or 12 channels, whatever it is. But this shows the proof of concept, I guess, on the animal experiment. So as you see, this is the bandwidth of our sensor. At 3 kHz, we shouldn't hear anything, so it shows that it's working properly. So what we have accomplished up to now, we finalized the sound transducer. They are working pretty good. But we have to increase the bandwidth. Bandwidth is an issue for high quality hearing. Energy harvester, we are still away from the desired energy harvesting value, but it's a big challenge as well. But 60 microwatt in air environment is not that bad, can be improved further. For the sound processing and energy harvesting ICs, I think we got the world record, like ultra low power signal processing system for such applications reported for the first time by our group, I guess. For packaging, we come up with our own techniques. They may not be that novel, but they are specific to this application. And to be able to do this test, we developed an artificial tympanic membrane where we can do some of the tests without killing any more animals. So we have 1.5 years more to go. At the end, we want to combine everything in a single package to be implantable and improve the performance of energy harvester and the PCT material for sound recognition. So this is the group. The beauty of the group is like they are from different disciplines, like electrical engineers, mechanical engineers, chemical engineers, medical doctors are also in the group. So I think that's the fun part of our research. And at the end, I want to thank my students and alumni from my group in past years. I present in here, but they do all the work in here. So I should thank them, I guess. And also our partners, Hacettepe and Gazi University Medical School, Ankara University Medical School, different departments from our university, and the funding sources. Thank you. I hope I'm on time and we didn't get bored.